Arguably, the greatest debate forged and fought by philosophers, scientists, religions, and humanity is about the origins of the universe. While even our most accepted scientific theories continue to evolve, others have opted for a linear approach. We tend to view these contending principles as opposing parties, fearlessly and fiercely going at each other's throats to prove the other wrong, a battle between supporters and opponents of the Big Bang Theory. Yet, we often forget that these ideas are theories, not proven principles. Not everything is set in stone. It is important to remember that the world doesn't only have two viewpoints about the universe's origins. New theories are emerging, like the idea of a cyclic universe, collapsing and rebirthing in an endless loop. We'll dive into the surprising physics behind the origins of the cosmos. We'll explore bizarre concepts like conformal cyclic cosmology, quantum fluctuations, and cosmic inflation. Can the extreme force of a cold, empty universe create the spectacular Big Bang? Was there anything before the Big Bang? Or did time itself begin then? Could there be a cosmic serpent swallowing its own tail? Is the Big Bang just a part of the universe's timeline? We will investigate the astounding theories about where our universe came from. This journey spans from the first flickering of the Big Bang all the way to the ancient Ouroboros symbol and quantum realms beyond our comprehension. Join us as we dive deeper. To truly understand what could have happened before, we need to first take a look at what happened during the Big Bang. Essentially, the Big Bang is a scientific theory that explains how the universe began to expand from a highly compact and hot state. There are different models of the Big Bang that describe how the universe developed over time, from its earliest stages to its current large-scale structure. These models explain a lot of things, like the presence of light elements, the background radiation called the cosmic microwave background, and the overall structure of the universe. The uniformity of the universe, also known as the flatness problem, is explained through a concept called cosmic inflation, which involves a sudden and rapid expansion of space during its initial moments. However, a major challenge in physics is that there is currently no widely accepted theory that accurately describes both quantum mechanics and gravity in the extreme conditions of the Big Bang's beginning. These models match the Hubble-Lemaître law, which says that galaxies farther away from us are moving away at higher speeds. Using the laws of physics, these models show that the universe was once very concentrated, with a point called the Big Bang singularity, where the fabric of space and time breaks down. In 1964, scientists found the cosmic microwave background, which proved that the competing steady-state model was wrong. The Big Bang models explain the cosmic microwave background radiation as originating from the high temperatures and density of the early universe. This background radiation offers strong evidence for the Big Bang theory, which is widely accepted in the scientific community. Based on how fast the universe is expanding, it's estimated that the universe is around 13.8 billion years old. While the Big Bang models provide a solid framework, there are still parts of the universe that remain unsolved. As the universe expanded and cooled, subatomic particles and later atoms formed. The unbalanced distribution of matter and antimatter that enabled this process is known as baryon asymmetry, but its cause is not fully understood. The initial elements, primarily hydrogen, along with helium and lithium, gravitationally collide to form the initial stars and galaxies. Astronomers then went on to study the gravitational effects of a mysterious dark matter that surrounds galaxies. This unseen matter seems to provide most of the universe's gravity, which is different from normal matter like atoms. Further measurements of supernovae indicate that the universe's expansion is actually accelerating, a phenomenon attributed to an unknown force called dark energy. The Big Bang models provide a comprehensive explanation for a diverse range of observed phenomena, including the distribution of light elements, the cosmic microwave background, the vast-scale structure of the universe, and Hubble's law. These models are based on two main assumptions: the universality of physical laws and the cosmological principle. The universality of physical laws is a central concept in the theory of relativity, whereas the cosmic principle suggests that the universe on a large scale appears the same in all directions and locations, a concept known as uniformity and symmetry. These concepts were initially conceived as hypotheses, but efforts were made to test them in the real world. The universe's large-scale appearance is isotropic when seen from Earth. The term isotropic refers to the existence of a physical property that displays the same value when examined in different directions. If this law of isotropy holds true, the cosmic principle can be derived from a simpler principle known as the Copernican principle, which states that there is no one particular observer or perspective. Everything would be identical in all directions. One of the common misunderstandings about the Big Bang Theory is that it completely explains how the universe came into existence. But the Big Bang Theory doesn't explain how energy, time, and space came to be. Instead, it focuses on explaining how the present universe came from a state of very high density and temperature. It's important to note that trying to imagine the Big Bang with everyday objects can be misleading. When we discuss the size of the universe at the time of the Big Bang, we're referring to the size of the observable universe, not the entire universe itself. Hubble's law states that galaxies beyond a certain distance will appear to move away from us at speeds faster than the speed of light. It is worth noting, however, that special relativity does not apply to motion beyond the expansion of space itself. Hubble's law describes the apparent motion resulting from the expansion of the space between galaxies rather than their motion through space. Here's where it gets interesting. In a recent episode of a BBC series, physicist Brian Cox warned that the impending cooling and fading of the final star was on the horizon. If it disappears, the universe will become empty and without any light, life, or meaning. However, the dimming of this ultimate star is only the beginning of an endlessly extended and dim era. Massive black holes will eventually consume all matter, then disintegrate into inconspicuous glimmers of light over time. The universe will continue to expand outward until even these insignificant lights become too dispersed to interact, resulting in a cessation of activity. However, is this really the ultimate destiny? Some cosmologists believe that a previous universe, cold, gloomy, and empty, resembling the one we'll enter in the future, may have been the catalyst for our own cosmic emergence. Let's look at how the idea of material, physical matter, came about. If our goal is to understand the origins of stable matter composed of atoms or molecules, we must recognize that such matter did not exist during the initial moments of the Big Bang or for a considerable period afterward. Even though we know how simple particles became complex matter once conditions cooled down enough for it to become stable, this understanding doesn't answer the question of whether something came from nothing. So, let's rewind even further. The first enduring matter particles were protons and neutrons, which together formed the atomic nucleus. After the Big Bang, these particles came out about 1/10,000th of a second later. Until this point, there was no recognizable form of material. However, by tracing back through physics, we can explore processes predating the existence of stable matter. This leads us to the period called the Grand Unified Epoch. Now we're moving into speculative physics because our experimental capabilities aren't enough to look at the processes of that time. A plausible hypothesis is that the physical realm consisted of the brief existence of elementary particles, including quarks, which are the fundamental building blocks of protons and neutrons. At this time, matter and antimatter were present in roughly equal amounts. Like a quark, each matter particle had its corresponding antimatter, a mirror image partner, nearly identical but differing in one aspect. However, matter and antimatter annihilate upon interaction, converting into energy and disappearing. This cycle continued. But how did these particles come to be? As per quantum field theory, even a vacuum, which we may consider void space, is brimming with activity in the form of energy fluctuations. The spontaneous appearance of particles can be caused by these fluctuations, only for them to vanish shortly after. This might seem like a mathematical thing, but these particles have been seen in many experiments. The vacuum of space-time is filled with particles that emerge and dissipate, seemingly out of nothing. However, this might simply indicate that the quantum vacuum is, despite its name, a form of something rather than absolute nothingness. Philosopher David Albert has raised valid criticisms of explanations of the Big Bang that suggest that something can arise from nothing in this manner. Now let's ask, where did space-time itself originate? This leads us to delve even further into the incredibly ancient Planck epoch, a time period so early in the evolution of the universe that even the most advanced physics theories fail to break down. This epoch happened just a tiny fraction of a second after the Big Bang. At this point, even time became susceptible to quantum fluctuations. Normally, physicists work separately with quantum mechanics for the microscopic world of particles and with general relativity for the cosmic scale. To understand Planck's time, we need a theory of quantum gravity that combines both. While we still don't have a complete theory of quantum gravity, we've tried things like string theory and loop quantum gravity. In these endeavors, conventional space and time are viewed as emergent phenomena, similar to waves on the surface of a deep ocean. What we may perceive as space and time result from intricate quantum processes at a deeper microscopic level, processes that might not align with our understanding of creatures embedded in the macroscopic world. Over time, our regular understanding of space and time breaks down, which in turn challenges our understanding of cause and effect. Although this is not the case, all potential theories of quantum gravity describe some form of physical activity during the Planck epoch, a quantum precursor to conventional space and time. Then, the question arises, from where did this precursor originate? Although causality may not function in a conventional manner during this period, it remains feasible to explain one aspect of the Planck epoch universe through the lens of another. At this point, even our most advanced physics can't give us definitive answers. We will not be able to give a definitive answer until we make more progress toward a complete theory of everything. Presently, we can say with confidence that physics hasn't seen anything come from absolute nothingness. To truly unravel the mystery of how something could arise from nothing, we would need to unravel the quantum state of the entire universe at the dawn of the Planck era, but all attempts to do this remain highly speculative. Some people suggest supernatural elements, such as a designer, but there are other possibilities within the realm of physics. These ideas include the idea of a multiverse with many parallel universes, or the idea of a cyclical model of the universe, where it goes through a series of births and rebirths. One of the most fascinating yet contentious theories about the origins of our universe comes from physicist Roger Penrose. In 2020, this Nobel Prize winner proposed the idea of conformal cyclic cosmology to describe a cyclical model for the universe. Penrose was intrigued by a peculiar mathematical connection between the extremely hot, dense state of the universe at the moment of the Big Bang and the predicted cold, empty expanse trillions of years in the future after all stars die out. These states become mathematically indistinguishable when taken to their extremes, according to his bold idea. Strangely enough, the complete absence of matter might have led to the formation of all the matter observed in our universe. According to this perspective, the Big Bang emerged from a state of near nothingness. Remaining matter fell prey to the insatiable hunger of black holes and was ultimately reduced to photons that vanished into the dark emptiness. In this way, the entire universe originates from something that, from another angle, appears to be as close to nothingness as possible. Although this nothingness is still a type of something, it is a physical universe, albeit unbelievably empty. How can the same state be seen as a cold, empty universe from one perspective and a hot, dense universe from another? The complex mathematical procedure, conformal rescaling, is responsible for the solution. This is a geometric transformation that alters an object's size without compromising its shape. The old cold state and the new hot state have matching space-time geometries. It might be hard to fathom how two objects can be the same in this manner when they differ in size. Penrose says that the idea of size is meaningless in these extreme physical realms. In these extreme states, size doesn't matter as much as time does. How often have you heard that now? It is important to note that both the cold and dense states exist on distinct timelines. Despite the fact that the cold, empty state persists indefinitely from its own temporal perspective, the hot, dense state it engenders occupies a new distinct timeline. Perhaps it would be beneficial to envision the hot, dense state as arising from the cold, empty state in a non-causal manner. Instead of a conventional cause and effect relationship, we might describe the emergence of the hot, dense state as springing forth from being grounded in or being actualized by the cold, empty state. These notions go into metaphysical territory, which has been extensively explored by philosophers of science, particularly in the realm of quantum gravity, where the conventional notions of cause and effect break down. Towards the limits of our understanding, the boundaries between physics and philosophy become increasingly difficult to distinguish. Conformal cyclic cosmology presents detailed but speculative answers to the origin of our Big Bang. Although Penrose's vision may gain support in the future progress of cosmology, it is possible that a more profound philosophical question will remain unanswered: the origin of physical reality itself. How did the entire system of cycles come into being? This leads us to the question of why there is something instead of nothing, a profound question in the realm of metaphysics. We remain focused on explanations rooted in the domain of physics. There are three main ways that cycles might have started. The first possibility is that there is no physical explanation at all, probably the simplest of the lot. The second idea is to repeat cycles indefinitely, with each cycle being a separate universe, and the quantum state of each universe's start being explained by some characteristic of the universe that came before it. The third possibility envisions a singular repeating cycle, with the beginning of the cycle explained by a trait of its own end. These last two options avoid the need for uncaused events, giving them a unique appeal. In these scenarios, nothing would remain unexplained within the scope of physics. The way Penrose sees things is based on his take on quantum theory, which leads to an endless stream of fresh cycles. In quantum mechanics, a physical system can be in many different states at the same time, and only when it is measured does it choose one state at random. According to Penrose, each cycle involves random quantum events, producing different outcomes, resulting in variations between cycles. By observing faint traces in the residual radiation from the Big Bang, the Planck satellite could potentially glimpse the pre-existing universe that gave rise to ours. Penrose and his colleagues believe that they have identified these traces, attributing patterns in Planck data to radiation from supermassive black holes in the previous universe. These claims have, however, been challenged by other physicists, leaving the matter unresolved. There is a way to shift conformal cyclic cosmology from a multi-cycle model to a one-cycle model, according to Penrose. In this case, physical reality involves a single cycle, from the Big Bang to a profoundly empty state in the distant future, and then back to the same Big Bang, resulting in the birth of the same universe once more. This possibility is in accordance with an interpretation of quantum mechanics, commonly referred to as the many worlds interpretation. According to this interpretation, when we measure a system in superposition, the measurement does not randomly choose a state. Rather, the outcome we observe is merely a single possibility, the one that unfolds within our universe. Other results occur within separate universes, within a multiverse, disconnected from our own. Even if something's unlikely to happen, it might in some quantum parallel universe. For example, you could have become a movie star, gotten swept away in a rare hurricane, spontaneously combusted, or even endured all three unlikely fates simultaneously. It's all possible. Our Big Bang might be the rebirth of one single quantum multiverse, containing infinitely many different universes all occurring together. Some individuals believe that these parallel universes might also leave observable imprints in cosmological data caused by collisions with our universe. The many worlds view of quantum theory adds a new layer to conformal cyclic cosmology, but Penrose doesn't agree with this view. According to this perspective, the Big Bang may represent the rebirth of a singular quantum multiverse, comprising an infinite array of distinct universes that are all occurring simultaneously. In this scenario, everything that is possible not only happens, but also happens repeatedly and endlessly. Pretty darn scary if you ask me. It reminds me of that time I bumped into my ex. Really don't want that to happen endlessly. Penrose's perspective is captivating, especially for a philosopher who is deeply rooted in science. It opens up fresh avenues for comprehending the Big Bang, expanding our explanations beyond the ordinary boundaries of cause and effect. It serves as a remarkable litmus test for exploring the diverse ways in which physics can illuminate our world. It deserves deeper consideration from philosophers. Penrose's cosmic cycling concept has parallels in ancient myths worldwide. The Ouroboros, a serpent eating its own tail, symbolized eternity and endless renewal in Egyptian iconography. Norse legends envision the world serpent Jormungandr encircling all lands. Modern physics now gives fresh meaning to these ancient cyclic symbols. The Ouroboros serpent, ingesting its own tail at the universe's end, spawns a new Big Bang from nearly nothing. Physicists explore reality through equations, while ancients relied on imagination, yet both pointed to cosmic cycles beyond our everyday experience. Without question, the Ouroboros within the paradigm of the one cyclic universe is majestic. The universe encompasses our own universe and a multitude of peculiar and fantastic alternate universes permitted by the tenets of quantum physics. Remarkably, at the juncture where its head meets its tail, it is simultaneously devoid of matter, yet teeming with energy, pulsating at temperatures reaching unimaginable levels, hundreds of thousands of million, billion, trillion degrees Celsius. Theories about the origins of the universe continue to evolve. While a cyclic cosmos is an ancient idea, modern physics lends it fresh perspective. Conformal cyclic cosmology may one day reveal more about the Big Bang's mysteries. For now, a fusion of science and philosophy is needed to comprehend reality's deepest questions. Physics takes us back to the tiniest fraction of a second after creation. Beyond that lies abstract metaphysics. The search for answers is ongoing. What do you think? Was there a time before the Big Bang? And does the cosmos go through cycles? Let us know in the comments below. Consider subscribing to our channel if you like this video, and as always, thanks for watching.